okay, if we have, if you have a Newtonian fluid, what does that tell us? It has constant viscosity, and so this, and what is the relationship between the viscosity and the shear stress? Proportional to what? Okay, and so the viscosity is constant for a Newtonian fluid, which makes it constant. So the shear stress is proportional to what? And what is the shear rate? The velocity gradient, right? All right. Okay, so we are remembering our fluid mechanics, right? Or fluid dynamics. All right, so we go on to, let's look at the momentum equation in the y direction. Okay, momentum equation in the y direction. And my question is, what is the body force rho F y? What would you say is the body force rho Fy? Yes. Gravitational force, assuming assuming G is in the y direction. Okay, so long as in your analysis you are saying that my y direction basically corresponds to downward, and so really what I'm trying to point out is that, well, in my analysis, I could choose my gravity as associated with Z or my gravity associated with Y. Okay? Depending on what I decide, then one of them must be 0, right? Okay. Now, let me also say that, the governing fluid dynamics equation are often put into non-dimensional form. What do we mean by non-dimensional form? For example, if you look at the independent variables in the governing equation, x, y, z, in those equations, and also time, okay, you can cast them as dimensionless. For example, dimensional x star, which will be the actual x divided by, say, the length of the pipe, okay, or a characteristic length. Again, y star will be y divided by a characteristic length y. Time will be expressed as velocity times time divided by L. We know that time over velocity is inverse of velocity, right? And so times u, that means that this T star becomes dimensionless, okay? Similarly, you can get dimensionless density and so on and so forth. And so we cast those equations into dimensionless parameters to take advantage in doing so of parameters such as the Mach number, okay, which is a dimensionless number, as we learned last class period. It's the velocity divided by the velocity of sound, the Reynolds number, the Prandtl number, and so on and so forth. That allows us to basically look at parameterization of your results, okay, in a non-dimensional form. So here is a problem, okay? You want to consider laminar flow, a laminar boundary value flow, that can be approximated with the following velocity profile. U of x is equal to uppercase U infinity times y divided by del. And del, which basically represents your boundary layer thickness, is given by Cx to the power 1/2, or square root of that. Okay? With reference to two-dimensional boundary layer flow over a plate, can you determine the velocity v, that is the vertical component inside the boundary layer? Let me see if I can quickly draw this. So we are saying that we have a flat plate, okay? Incident on the flat plate is a fluid flowing over it. The arrow doesn't want to stay. Anyway, and then as a result, you have a boundary layer developing such that that is the thickness of the boundary layer, and the velocity then would be varying through the fluid Okay, so we have, this is a flat plate or a flat surface. With thickness into the plane of the page. Sorry for my unsteady hand resulting in crookedness. But this is a flat plate, flat into the, into the page, and then you have a fluid flowing over it. As a result, you have a boundary layer being developed, and the thickness of the boundary layer del is given by C x to the 1/2. The velocity u of x, this is u of x is this quantity which flows over the plate. Now, why am I showing that at this point the velocity is, say, 0? Okay? Because of no slip, okay, we are saying that on the surface the fluid sticks to the plate when it enters, and so with time, as the flow moves and causes shearing and all that in the fluid, the boundary layer then would grow by a value del given by C times x to the 1/2. Okay, and so with reference to this two-dimensional, it's a two-dimensional boundary layer over a plate, determine the velocity v, the vertical component. We know the u component, and so we can find the v component of the velocity inside the boundary layer. So my question is, how can we find the velocity inside the boundary layer? What have we learned today that can help us find the velocity inside the boundary layer? Now we move to the third row. What have we learned today that can help us find the velocity inside the boundary layer? What conservation equation can you use? We can use conservation of mass. Okay, we can use conservation of mass. Knowing that the velocity, you have a laminar boundary layer, and you have the following. If you look at the velocity profile in the x direction, is it time dependent? There's no t term, right? So there's no time dependence. Okay, so if I go back to my conservation of mass, my continuity equations, okay, so for our problem, which of these terms have to drop out? Okay, this has to drop out. And what else? The z direction also has to drop out because we are told it's 2-dimensional, right? So we are only left with these two terms. Okay, we are only left with these two terms. And if we say that the density is constant, we factor out the density, then that means that the partial for our problem for this problem, then we can say that du dx plus dv, I'm struggling. Okay, has to equal 0. Okay, du dx plus dv dy has to equal 0. Are we clear? Okay, so now, since I've shown you, we've solved almost half of the problem, okay, can we find the v velocity? The velocity component in the y direction. Can we find the velocity component in the y direction? Pardon me? Yes, they are partial derivatives, yes. What is the trick to finding the velocity in the vertical or the velocity in the vertical direction, the v velocity? Yes. Yes, we first have to find partial du dx. Okay, because as you see, we know that we want to find this v, right? So if we bring du dx to this side of the equation, that gives us v by its on this side, and then if we integrate on that, that would give us the solution. And so what we have to do then would be to say that, and let me see if I can struggle through this here, and say that this is v is equal to the integral of minus du dx times dy. Okay, now do we know du dx? We can find it. We have to, first of all, substitute for del in u of x, right? Once we substitute for del with c times x to the 1/2, then we can take the derivative of the partial derivative of u with respect to x and substitute into that equation and then integrate it. Okay, so that's a homework problem. Any comments or questions? Okay, so let me now transition to go over the energy equation quickly. Okay, we know that energy has to be conserved. And the rate of change of energy within the control volume is equal to the net flux of heat into the control volume plus the rate of work done by the body forces and surface forces, right? Whenever you have force that tends to move an object, or in this case, a fluid, you're going to have work done. So your body forces, your pressure forces, your shear forces are all doing work on the fluid element. What are these forces? Well, what does the conservation of energy boils down to? From the statement of the conservation of energy, we are saying that A is equal to B plus C, where B is the net flux of heat into the control volume, and C is the rate of work done by the body, by the surface body and surface forces. We identify A as the internal energy of the fluid per unit mass, and also the kinetic energy of the fluid per unit mass. Okay, so that is our A term. And so the substantial derivative of the internal energy as well as the internal energy as well as the kinetic energy gives us the A quantity. And then B, the volumetric heating rate of the fluid per unit mass would be Q dot, and the conduction of heat in all the three directions, let's call QX, QY, and QZ. Okay? C will consist of work done by the body forces and the work done by the surface pressure and shear forces. We look at this complicated control volume and try to identify all those forces. Okay, so for example, if we look at this phase here, 5, 6, 2, 1, okay, we will identify the work done by the normal force tau xy, okay? The force, you see, stress times area gives you force, right? Times the velocity gives you the work done. Okay, so that's the work done in the x direction by that normal force. And then we are saying that, well, you will also have conduction of heat into the volume through the phase. Heat conduction acts normal to an area. Okay? And then you also have the pressure force tending to compress the fluid. So Pu dy delta y delta x. Okay, that is times U gives you the work done. Pressure times delta y delta z gives you the force, and then times U gives you the work done in the x direction. Okay, and now you also have the shear component, and so on and so forth. And then, of course, then you have on the other side, you have the differential amounts that would impact the change in energy within the control volume. Okay, so if we sum up all these terms, noting that a force acting in the negative direction does negative work, well, this is your B term here. Okay, this first term represents the volumetric energy generation within the fluid. Okay, and then you have here your conduction terms. Okay, and then if you add for the x, y, and z direction, you end up with this term here. Then you go to your work terms. The work terms in the x direction are all these equations. And then you have, of course, the body force work term, which will be reduced to this last equation down here. Okay, this is nothing but taking the sum of all these energies and putting them into each of these equations, B and C, to result in that. We do the same for the y direction and also for the z direction. And then if you add all the three equations together, you end up with this big equation. And so you can end up with a statement of the energy equation. On the left-hand side, you have the substantial derivative of the rate of change of the internal energy and kinetic energy being equal to the Q dot, which is the volumetric energy change within the volume, minus the conduction terms within the fluid, and then you have plus the work terms, body force and shear force terms, plus also the pressure terms. Okay? And in a more compact form, this will be your energy equation. Comments or questions? Yes? Okay, so in this case, we are assuming that the fluid is at the same elevation. Okay, so note that, in all these problems, I go back to the momentum equation where in our initial derivation, we said we are neglecting electromagnetic force and we are neglecting electrical force in the field. Okay, so here again, I didn't say it, initially we are neglecting potential energy as a contributing force. All right? And so we can write our energy equations in this more compact conservation form. And so far, we haven't accounted for the viscous terms, that is the taus. Okay, we haven't accounted for the viscous terms. But now we can account for the viscous term. And then note that the Q term here, Qx, Qy, and Qz, has been replaced by K delta T dx, okay, which is what law? Fourier's law, okay, Fourier's law of heat conduction. Okay, we introduced Fourier's law of heat conduction in the 3 dimensions. Now let's see, to take care of for Newtonian fluids, our normal shear would be given by these relations. Sorry, the normal stress is given by these relations, and the shear stress is given by these relations at the bottom. So, as you can imagine, if you end up substituting these tau xx and so on and tau xy terms into this equation, then it becomes very complicated. Okay? In a number of your textbooks, such as in chemical engineering, you guys use transport phenomena, right? By Bird, Stewart, and Lightfoot, right? I think Dr. Boakye, you used that book to teach your transport phenomena. No? It was what? Oh, okay, but whoever taught you may have used that book. Okay, the transport phenomena. Well, I guess what I'm saying is that, yeah, I'm not going to commit this to memory. In those books, you have the reference sections, the appendices that has all of this captured in it. Okay, the important here is for you to clearly understand how these equations were derived and where they are coming from, and so that you will make the right substitutions in them when you have to apply them. All right? Yeah, we see viscosity here, and so the question is, what do I use for viscosity? Well, Sutherland gives us a viscosity law saying that the viscosity is a function of temperature. Okay, the viscosity is a function of temperature, And so some constant temperature at some viscosity at a reference temperature 0 if once you vary that temperature, you should be able to calculate the viscosity of the fluid, okay? So that then will be substituted, this relation will be substituted here, and these tau terms will in turn be substituted into the momentum equation. So these are your fluid flow governing equations. Your continuity equation in weak conservation form. You have your x momentum, your y momentum, your z momentum, and then in this compact form that we call Cauchy's equation. Okay, making use of your del and divergence operators. Okay, and again, these are all summarized in your transport phenomena textbook. That was your continuity and momentum, and now this is your energy equation. Note that if you identify all the source terms in the governing equation, that is the continuity, momentum, and energy, okay? Notice also that each term in the continuity, momentum, energy equation represents mass rate per unit volume. Okay, mass rate per unit volume, momentum rate per unit volume, and energy rate per unit volume with those requisite units. And so we can simplify all these equations, for example, for steady state flow with constant properties. Okay, for steady state flow with constant properties. If we are to simplify the momentum equation for steady state with constant properties, okay, what do you think would happen to the first terms here, the local? It will be 0, right? Steady state. So that goes to 0. Okay? And then also, we have constant properties, so you can basically factor out the densities. Okay? Constant properties also affects what? The viscosity. Okay? So that viscosity can also be factored out. Okay? So this is how you have to think of when you are manipulating these equations. And I'm stressing this at this point also that now, you see, when you go into your fluid CFD software, you see various control input panels or input, input panels that you have to specify. Well, it's my system steady, it's my system constant properties, I mean, am I solving the energy equation or am I solving the momentum equation or not? Okay, that is when you are doing this by selecting, those icons or those panels. Basically, you are saying that, well, let me turn this part of in the equation. Let me basically factor out my viscosity in the equation, and so on and so forth. Okay, so some pattern comments here, okay, before I go into the boundary conditions. The same set of equations are used to analyze any fluid problem, Okay, so any fluid, water, air, any fluid problem, you use the same set of equations. Okay, now the specifics of the problem boils down to identifying what your initial conditions are and what your boundary conditions are. Am I solving the problem for just a fluid in a tank, which is spherical, or a flow in a pipe? Okay, that would impact my initial and boundary conditions. Okay, the governing equations can be written in conservation form and non-conservation form. Okay, and I give you the example of the non-conservation form. Non-conservation form. Okay, the governing equations are coupled and non-linear. Okay, let me go back and stress the non-linear part. Okay, so for example, if you substitute velocity in your momentum equation, your viscosity is a function of temperature, right? So it makes the differential equation nonlinear. If your thermal conductivity is a function of temperature, it will also make the energy equation nonlinear. Your normal and shear stresses are functions of the velocity gradient, particularly Newtonian fluids. And then for a three-dimensional problem, there are 6 unknown variables, right? Density, pressure, your 3 velocities in the x, y, and z direction, as well as your internal energy. So you have 6 unknowns in the governing equations. However, you only have 5 equations. Right? You have your continuity equations, you have your 3 momentum equations, and you have energy equations. How can you solve it when you have 6 unknowns and you have 5 equations? Well, you can do that if the 6th equation is therefore required by using, for example, if the air is an ideal gas. Okay, so you use rho RT to basically replace pressure in the equation. Okay, therefore eliminating the P term. Okay, and you replace the E, internal energy, with your specific heat at constant volume times temperature. Okay, so yes, there are various simplifications that can be derived in solving these equations, whether by pure analytical means or by computational fluid dynamics. You just have to understand the fundamentals of the problem in coming up with your solution. Any comments or questions? Well, you just have equations, okay? We just have 5 equations. As we learned in our calculus class or our differential equation class, given a differential equation, you need boundary conditions to solve it, okay? And so what are the boundary conditions that are needed or one can use to solve the flow, say for flow over an airplane, flow through a pipe, or flow over an athlete, or numerical weather prediction, and so on and so forth, okay? Here are some examples of boundary conditions. One, you have the no-slip conditions for viscous flow. That is, the fluid particle in the neighborhood of a stationary body basically is fixed, stationary. Okay, number 1. The fluid in contact with the surface has a velocity of 0. 2, we can also assume that the wall temperature is given. Okay? If the wall temperature is given, that doesn't mean that your heat flux is known. Another form of boundary condition, or let's go back. Can anyone give me an example of when you know, say, a wall temperature? Yes.
If the wall is some source of heating, the wall is
okay. Yes. So you would measure the temperature based on the heating that is applied. Okay, so and your measuring devices are your thermal sensors, thermometers, thermocouples, flux sensors, and so forth. Okay, or infrared sensors, temperature sensors. Another type of boundary condition is the constant wall heat flux. Okay, if you apply a heat flux to it, to a wall, then you know that is a boundary condition. Okay, for the case of adiabatic wall, okay, the heat flux is 0. Okay, what is an example of an adiabatic wall? Or physically, how can I represent an adiabatic wall? In other words, there's no heat loss from the wall. How can I represent that if I want to? I'm a designer, and I'm required to make sure that there's no heat loss from the wall. You insulate it, okay? You insulate it. That doesn't mean that you're going to get perfect heat loss, but we know that insulation will basically prevent substantial heat loss, okay? So we assume adiabatic wall or 0 heat flux, and in that case, the temperature gradient is 0, okay? And another type of boundary condition is also the symmetric conditions. If you are assuming a line of symmetry, then the primitive with respect to the normal is 0. The partial of the symmetry with respect to the normal is 0. For in-visit flow, that means that your viscosity is also 0. Okay? For in-visit, your viscosity is also 0. So here, the key thing is that we have to know the proper boundary conditions in order to obtain good CFD solution. Okay, just like we will have to know the proper boundary conditions in order to get good analytical fluid results or experimental results. Okay, if you are to conduct chemical reaction in an insulated environment, that means with no heat loss, and you don't insulate your vessel, that means that you're not applying the right boundary condition. Okay, so experiment-wise, you're not going to get the right result in terms of the chemical process. Similarly, in the CFD computation, you're not going to get the right result. Now, for us CFD practitioners, softwares such as ANSYS has a number of boundary conditions inbuilt within the software. Okay, that again, we just have to click and select. And these conditions are wall, mass, flow inlet, mass flow inlet, mass flow outlet, pressure inlet, pressure outlet, and so forth. I will entreat you to Google answers fluent boundary conditions to learn more. Comments or questions? Any comments or questions? Okay, so let me stop here. Now that we have some understanding of what these conservation equations that may apply to a given CFD problem and how to basically turn them on or off depending on need of solution, then the next step of the CFD problem is, okay, we have this conservation equation. How do we do the numerics, or how do we convert these conservation equation into discretized equation so that we can solve them algebraically? Okay, so we can solve them algebraically. So I want to spend another lecture talking about finite differences, the finite difference methods. Or comments? But by the way, even though I'm not tasking you to derive these equations from scratch, if you are interested in postgraduate studies, it's very good practice to go through the derivation at least once. Okay? And in fact, you'll be expected to do so. Yes?
Prof, I learned that the Navier-Stokes equation can be used to solve any fluid flow problem. So now I want to know, in case I have a fluid flow that does not have some boundary conditions, that like I want to know, can the Navier-Stokes be used to solve like all fluid flow problems?
Every flow problem has to have some boundary condition. Now, what you are probably thinking about is, you see, it depends on the type of flow. Now, let's take flow over an aircraft. Okay? Flow over an aircraft is an external flow. Okay? So the boundary of the flow would be the surface of the aircraft. Okay? Would be, the surface, and so anything above it, well, it's open to the sky. And we know that far away from the aircraft, those boundary layer effects, those environmental effects will not impact the aircraft. What impacts the aircraft most will be the fluid in immediate contact with the aircraft. Okay? And so that is what will be what you have to consider most important. But you cannot say that there are no boundary conditions in solving Navier-Stokes equation. You always need boundary conditions. Other comments or questions?
I thought you were going to ask the question of, there's this story moving around, and no one is going to solve the Navier-Stokes equation, but you are saying that you are going to solve it. If you can do something, light on it.
When you say that no one has been able to fully solve the Navier-Stokes equation, Yes, we solve it making simplifying assumptions. Okay? We solve it using simplifying assumptions. Now, to not be able to solve it, well, what is the application? For me, the question is, what is the application? And can I make some simplifying assumption to really solve it? I know, as an engineer, we are always looking at an applications. And we are always looking at, okay, in my application, can I make some simplifying assumptions that will give me some reasonable solution for the problem at hand. But, solving the Navier-Stokes equation for the sake of solving, like I said, you have what? How many equations? You have five equations. How many are known? 6. Can you solve that? No. Okay? No, you can't. So you can only solve it by introducing some constitutive relations to help you solve it. Yes?
The governing equations we looked at were for fluid flow problems. So the question I have is, if there are multiple fluids, like a multi-phase problem, do we solve like a different set of equations for the different fluids, or do we lump all the fluids into one system and say maybe the continuity equation governs every fluid in the system?
Okay.
Like assuming one is a gas and one is a liquid, or even maybe if there's a solid in the system.
Very, very good question. Very good question. Okay, so now you are talking about multi-phase flow. Okay, so in multi-phase flows, okay, you can basically, depending on the nature of the flow, well, you can have a 2-component multi-phase flow, let's say air and water, which are not miscible, okay? In which case, yes, you have to solve the equations you have to come up with equations for each of the phases, for the air and for the water. Now, there will have to be a constitutive equation that couples the two together, okay? And so I haven't talked about that, but so in multi-phase flow, then you have to come up with that constitutive equations that couples the interface of the two together. Okay? On the other hand, if you are solving a single component fluid such as water and its vapor, then in the conservation equation, you basically have to resort to the phase change equations to help you solve it. Okay, so part of the solution may involve solving the problem as water, and part of the solution will involve solving the vapor in the form of its vapor. Yes?
Can something like, let's say, a two-film theory. Two-film
Okay.
theory. When I remember this year, this film where you had this emotion phase and
Okay.
kind of some gas phase. So you're kind of solving them separately. And the only thing you're doing is, if there's diffusion from one phase to the other, that's what you account for. Or if there's temperature, like the heat transfer, is that what we do here?
Oh, okay, so the point is, okay, what if you have diffusion occurring across interfaces? Again, that is the coupling that is required. You need a coupling relation. Now, in solving these equations, we haven't turned on the diffusion equation. Okay, conservation of the generation of mass transfer. Okay, so once you turn that part on, that basically couples the two different phases also together. Yes?
Is it like adding and subtracting source things? Maybe from the equations for the different
Yes. Yes.
So I'm thinking, assuming there's evaporation.
Yes.
Liquid phase. So do I add a source term to maybe the...
You will have to add a source term.
So
okay? The source term will account for what the rate of evaporation or the rate of condensation of one phase over the other. Okay? So there has to be a source term that couples the two phases together. Any thoughts, any doubts? Yes. Does it account for? Okay, so the source term would appear in the governing relation. For example, let's take heat conduction. Okay, if you've taken heat transfer, then these terms here are all volumetric effects. Okay, these terms here are volumetric effects. What does that mean? That means that it's an internal energy generation term. Okay, and so that internal energy generation term could be an exothermic reaction or an endothermic reaction that can add heat or remove heat from the system. Okay, and so that is how you account for those terms in the equation. So examples of source terms would be in a nuclear reaction, okay, whether you have fission or fusion, you have internal energy generation that is taking place that has to be accounted. Or let's say that you are doing a process reaction and you insert a heating system into the fluid or into your process tank, okay, resulting in internal heating of the fluid. Okay, that is also heat source in your process that you have to account for. Other comments? Okay. Thank you for your time and your attention. We'll wrap it up with the finite difference and then looking at a case study of one of my graduate students' research work. Yeah. Yes. Yeah.
Will be the PDFs from you for the first lecture.
Yeah. Yeah. Yes, I'll send it. I'll send it to Patrick. Yeah.
The other thing is, if you could give the signature, we wanted to do this certificate, and I've been asking Patrick.
Oh, okay, yeah.
If you can, I can take a picture and send it to the guy who's.
Oh, who is doing it? Yeah, yeah.